Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to talk about gravity. We're going to start by recapping what we understand about non-contact forces. We're going to look at what we mean by the gravitational force. We're going to look at the factors that affect this gravitational force, which is the technical word we use to describe gravity. We're going to look at the concept of gravitational field strength. We're going to then bring that together with the concept of what we understand about weight and how do we calculate weight as a force. So we're thinking about this within the context of forces. We thought in the past about forces being contact and non-contact. If this concept is something that is unfamiliar to you, you might want to check out the types of forces video that I have on this channel, or some of the other videos that I've made around magnetism and electrostatic forces, just for a bit of that context. But non-contact forces are those that can be applied without any contact between the two objects. That is, they can happen at a distance. So we have looked previously about magnetism. We can also, today we're thinking about gravity or the electrostatic force as well, what we understand about static electricity. Examples of forces that can act at a distance. So now let's understand more about the gravitational force, that is, gravity. So gravity is an attractive force. That is, it's not a pushing force, it's always a pulling force. It's a pulling or attractive force that exists between objects that have mass and causes them to attract towards each other. Relatively speaking, it's not a very strong force compared with some of the other forces we encounter in our everyday lives, but it still has a noticeable effect on us. And it has an effect on us because objects that have mass create a gravitational field. That is the area around that object in which gravity seems to just work. That it has an effect, and so we can see that gravitational field is affected by a couple of different things, but it causes falling objects to accelerate. Now, so if you have, say, like this apple, and you hold it in the air and then you let it go, what's going to happen is that it's going to move towards the ground, but it's going to be speeding up all of that time because of this force of gravity, this attractive force towards the ground. Now, as we seek to understand a bit more about the gravitational force, we can see that it's actually objects accelerating towards one another, even if that can be very difficult to see from both sides. But essentially, we can see that behavior happening, especially with big objects like planets around the sun and so on. But so it causes acceleration. And so the factors that affect the gravitational force, there's two main things that will affect the strength of this, or the size or magnitude of this force between them. Firstly, the mass of each object, and secondly, the distance between their centers. So we say that this attractive force is acting at the center of mass of each object. So how far apart are they, and how much mass does each object have? So firstly, let's think about the impact of mass. So if we take an object where we've got two 1 kilo objects and they have a gravitational force between them, and then for one of these objects we increase its mass, so we see a 2 kilo mass or a 3 kilogram mass, that the gravitational force between them increases as the mass of those objects increase. Now, if we notice that the second object on the right increasing as well, we'd see an even greater effect on the gravitational force as both objects were getting larger and larger. So this is why I say that even though gravity is actually a relatively weak force, that we still feel its effects because we're often interacting with very, very, very large objects like the Earth beneath our feet. But so the mass of each object, the larger that one or both of them are, the greater the gravitational force. But what about distance? So if we take the same two objects, the same 1 kilo objects we looked at before, and we bring them closer to one another, we can see that the gravitational force, that attractive force between them, gets stronger and stronger. So the closer they are together, the closer their centers of mass are, the stronger the gravitational force. And so now we come to this concept of gravitational field strength. That is, let's think about how strong this is in relation to this gravitational field. So the definition that we're talking about here is how much force the gravitational field of that object exerts, that is, applies or causes to happen on each 1 kilogram of the object that's being affected. So we use units of newtons per kilogram. Notice with this to the -1 is the same as newtons/kilograms. It's just a little bit more mathematically precise to write it that way. So newtons per kilogram. So on Earth, the gravitational field strength is 9.8 newtons per kilogram. So what that means is that if we have an object, I'm going to show you kind of using this grid sort of section to say each box represents 1 kilogram of the mass of an object. So if we have a 2 kilogram mass, that then each kilogram of that object, let's divide it up. Each kilogram is experiencing 9.8 newtons of force. That means that that object in total is experiencing 19.6 newtons of force. That is 9.8 times 2. If the object had a 5 kilogram mass, let's do the same thing. Each kilogram of its mass is experiencing 9.8 newtons of force. So in total, it experiences 49 newtons of force. What about if it's smaller than a kilogram? So half a kilogram. Well, for every kilogram, it would experience 9.8 newtons. So half a kilogram is going to be 4.9 newtons. That is half of 9.8. So we can see that we can calculate the total amount of force an object is experiencing because of that gravitational field. But what happens if we go to different places in the universe? That the Earth has a certain number, but other objects are different. So we can see the Moon, Mars, Saturn, Jupiter, and even the Sun. All of these have very different gravitational field strengths. Some, like the Moon and Mars, are lower than Earth's. Others, like Saturn and Jupiter and the Sun, this is just a selection, are much, much larger. These values vary with different space objects like planets and moons and things like that due to their differing masses. That is, the Sun and Jupiter have a much, much larger mass than the Earth, so the gravitational field strength is a lot stronger. And so the larger mass creates a greater gravitational field. But what's the total force going to be on the same object with the same mass in different gravitational fields? We're going to apply the same sort of way to demonstrate it here, using each grid representing a kilogram of mass. So if we consider a 4 kilogram mass object on Earth, each kilogram experiences 9.8 newtons of force, so in total that object experiences 39.6 newtons of force. 9.8 newtons for each of those kilograms. But we take that same object and we put it on Jupiter. Jupiter's gravitational field strength is 26 newtons per kilogram. So each kilogram experiences 26 newtons of force now, so the total force is now 104 newtons for exactly the same object. What about if we went the other way and we took it to the Moon, where we have 1.6 newtons per kilogram, so every kilogram experiences on that 1.6, so in total it's only 6.4 newtons. It's significantly lower than on Earth. So it helps us now to then think about, well, we've been calculating this force in this kind of way. What do we call this force? Well, we call it weight. So weight is the technical, even though we use this word in everyday life in lots of different ways, what we're describing is the force of a gravitational field on the mass of an object. Essentially, if we kind of simplify it a bit, we're saying how much force is acting on an object due to gravity. So weight, even though in an everyday context, how big something is or how heavy it is, but in the science context, we give it a particular meaning. We're referring to something very specific. This weight is a force that's directly proportional to the gravitational field strength that object's experiencing. Now, for most of the things we're going to be talking about or thinking about, we're here on Earth, where we've got a constant gravitational field strength. But we've just seen that then it varies depending on where you are in the universe. So the bigger the gravitational field strength, the bigger the weight for the same mass object, for a given mass. Okay, so this is why astronauts who have travelled to the Moon experience much less of this weight force, because the gravitational field strength of the Moon is lower. So they can jump higher, they can run further, they can bounce with greater distances. They hit a golf ball and it travelled a lot further on the Moon than it would here on Earth because of this difference in weight. Now their mass has not changed. They don't have a difference in the number of particles in their body, but the weight force due to the gravitational field is different. But how do we calculate weight? Well, there's a particular formula that we can use here. So this formula or equation, that is the weight of an object equals its mass times the gravitational field strength. So each of these quantities we give it a symbol, W for weight, M for mass, and lowercase g for gravitational field strength. So it's W equals M times G. and these are the units for each of those quantities. Newtons, kilograms, therefore newtons per kilogram. I'm going to show you an example now of how we might do this. Okay, so what is the weight of a 50 kilogram object on Earth? Well, we've got mass is 50 kilograms. The gravitational field strength on Earth is 9.8 newtons per kilogram. So we're using W equals m times g. We're going to substitute each of those numbers in where we see them. So 50 for m, 9.8 for g. And so then we put that in, and then we calculate a weight of 490 newtons. Okay, so the weight of a 50 kilogram object on Earth is 490 newtons. That's the force that object is experiencing. And that's weight. Okay, so what we've looked at in this video, we've reminded ourselves about non-contact forces, and we've looked at the idea of gravitational force and the factors that affect it, the mass and the distance between those two objects. We've looked at gravitational field strength and seeing how the mass of the object causing this gravitational field changes how strong that is. We've looked at how the effect of this gravitational field on an object is technically known as weight, and we've seen how we can calculate that. Alright, so thanks very much for watching. Don't forget to like and subscribe. Bye for now.